Hi, my name is Abrar. This is Lab 2, Lines of Charge. So in Lab 1, we calculated the excess charge on one piece of charge tape. One of the big assumptions we made was we assumed that all the charge is located at one point as a point charge in the middle of the tape. In this lab, we will be calculating the charge on the tape as a distribution of charges on a line using the formula provided. The concepts covered in this lab are Coulomb's law and the superposition of small charges as a line charge. So the procedure, in this part, we determine the force exerted by one U-tape on another when they are a measured distance vertically apart. By making two simplifying assumptions, use this force to determine the approximately amount of charge on one tape. So to do this, we attempt to position the two charge tapes above one another. Keep decreasing the distance until you feel like the top tape is floating. Measure this distance. We note that the only vertical forces acting on tape B is electric force due to A and gravitational force. We also assume that each U-tape has roughly the same charge, which simplifies the equation we'll need to calculate the electric charge Q on the tape B. Using our calculating gravitational force, we can solve for Q. The assumptions. So in our calculations, we assume that the charge in the long pieces of tape are split evenly into n charges. The larger the n value, the more precise the calculations. Each U-tape made has approximately the same amount of charges evenly distributed throughout the body. We also assume that each U-tape has roughly the same amount of charge. And to calculate the approximate mass, we're going to use the tape's length and density. So calculations. Here are data recorded from Lab 1, which includes the length, width, the distance, and the weight, and the procedure we're going to use for our new model. So we're going to iterate over small charges to find net electric force. We're going to compare the magnitudes of net electric force on top tape and gravity, and adjust the tape charges accordingly so that the magnitudes are equal. So here's our model. The red arrows represent the electric force pointing upwards on the piece of tape. The green arrows represent the gravitational force pointing downwards. The multiple arrows show how the line charges are distributed along the surface of the pieces of tape, and the number of lines depend on n. So here's our line of charge function. So this function divides the line into n equal sections, each with the properly scaled charge. These lines will be visualized into the model of the system. The greater the n value, the more accurate the calculations are. Now we'll need to calculate the electric forces and attempt to visualize the electric fields present. For every charge on the top line charge, we're going to iterate over each charge on the bottom line, summing each electric field for that top charge. Then we're going to sum these net charges for each top charge to find the net electric field on the top tape itself. This is done by nesting two for loops and doing vector addition at each step. Observations. So we notice that as we increase the value of n, the approximation slowly becomes more accurate as the line charges are distributed more evenly as n approaches infinity. To get the same calculation, we will have to take the integral of the function where charge q becomes dq. So instead of the sum of infinitesimal charges, we could take the integral of the surface area of the tape. The reflection. So one question we can ask ourselves is, what if we have modeled your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with our line charge model. So using our single point charge, the value we got was negative 1.46 e to the negative 8 coulombs, and using the line charge model, we got negative 5.72 e to the negative 8 coulombs. So the line charge model's value is 3.9 times greater than the value from the single point charge. Now we can ask, why do these estimates differ? Which value is more likely to be closer to the real value, and why? So the line charge model and function takes into account the distance between every small charge according to n, not just between the 2 point charges at the middle of the tape like in lab 1. So if you have more point charges that we're calculating the distance for, we're going to have a greater value of the electric force. The line charge model, therefore, yields a more accurate result as it uses a more realistic model. Thank you.